is of relevance here. So what we need to find out is what's the mass flow rate versus pressure drop relationship for a Newtonian fluid of constant viscosity mu. Now we know that for a tube or a pipe of constant cross section, it's the Hagen-Poiseuille equation which I taught you in fluid mechanics, which relates the delta P with mass flow rate. But here we have the additional constraint that there is a slight taper in the tube. So what is in the next paragraph I expressed what is known as the lubrication approximation. So as I mentioned, a flow between non-parallel surfaces can be treated as flow between parallel surfaces. So what would be the advantage of doing that, we would see later, but that's known as the lubrication approximation. And it's true only if the angle, or rather the change in R from the entry to the exit, is rather small. So we also know that from the Hagen-Poiseuille equation, the mass flow rate, which is denoted by W, and the delta P, they are related to the radius of the tube through which the flow takes place. And of course, it's inversely proportional to the viscosity for a given pressure drop, inversely proportional to length, and so on. And therefore, the pressure drop per unit length, and when I say this delta P, it's essentially P1 minus P2, or rather P at this point minus P2. But when we write it in the form of dP dz, then it's always going to be by definition the P final minus P initial divided by the length divided by the distance between these 2 points. So just I'm saying it once again, so that you remember that delta P and dPdx, delta P by L and dPdx, they are related by a minus sign. That's all, nothing else. So the pressure drop per unit length, it's straight away from Hagen-Poiseuille equation. So with this, now we are going to see that the problem here, or rather the additional constraint that we have, is this R is not going to be a constant. So what we can write then is, instead of delta P by L, I'm going to write minus dP dz, as I mentioned, the relation between them. So this is going to be 8 mu, the W that will obviously remain constant due to equation of continuity. The difference that we have here is this R is going to be a function of Z. So that's my, if I call it this as my equation 1, then this is my equation 2, which simply recognizes the fact that R is a function of Z. And in order to evaluate this RZ, how does R vary with Z? We go back to the geometry, the one that we have shown here, shown in the figure. So RZ, the resistance, if I do a linear variation, linear approximation, it would be simply that's straightforward, which we can write. So it's a linear variation. If we assume that, then the variation of radius can be written in this, and therefore dr dz from this equation would simply be RL minus R naught by L, which I call it as my equation 3. So these 3 equations, and then we need to bring in the pressure as a function, the pressure as a function of R. This is something which I would like to evaluate. Now, if I do that, if I use equation 2 and 3 together, then this equation and 2 and 3, maybe I go to the next page. Then of course this minus dP would be, it's just a substitution of what we have in conceptually in there. And you are, I would advise you to do it on your own, just to make sure that the algebra is correct. So if I integrate this equation, The apparent use of this exercise would be clear to you when we go to the final equation, final form of the equation. It would be even more clear to you that what would be the lubrication approximation and how would that give us a correction factor to be added to Hagen-Poiseuille equation in order to obtain the mass flow rate. But I am going to integrate it between z equals 0, that means at the entry, to z equals L. And I understand that at z equals 0, it's going to be equal to the radius is going to be equal to R naught. And over here, the resistance is going to be equal to RL. So it's a question of simple integration between the limits of pressure at the entry point minus pressure at the exit point. And just a rearrangement of the terms, or in fact, not even rearrangement. This equation simply gives me this is going to be my governing equation. So this is going to be my final equation. Now I go back to the I do this leave this integration to you. I'm simply going to write the final form of this. The part The purpose of this is simply to show you that sometimes the approximation, lubrication approximation, which is quite common, can give us so this is going to be the final form of the mass flow rate. I do not know why again this horizontal red line appears. I am extra careful after you have pointed out that this is due to my wrist touching the screen, but it still does. Probably I'm doing something wrong. It doesn't matter. I mean, obviously I did not cut anything. This is what we get as the mass flow rate. Now, if you go back and compare it with what we have over here, this specific form where W is pi delta P 8 mu L rho times R to the power 4, and compare that with this where this is R naught to the power 4, what we find out over here is that due to the slight taper of the surface, this additional term inside the third bracket appears automatically in the final expression. So this expression, this one, is commonly known as the taper correction to Hagen-Poiseuille equation. And of course, whenever we do that, we have to keep in mind is that this is only true if the variation is small. It is true when the variation in radius can be approximated by a linear relation between the entry and the exit. So the first part of the term is simply for a straight tube, and the correction factor is for the tapered tube. But once again, the analysis hinges on the fact that Navier-Stokes equation can be used. This form of Navier-Stokes equation can simply be used to obtain the mass flow rate for a tapered tube as well. Is there any question that you would like to clarify? Any point that you would like to clarify? Okay, so I leave this and then I come to come to a slightly different problem. I mean, it's slightly more complicated by the presence of motion of the bottom plate. So this is some sort of a belt which is moving, and the top plate is obviously, as you could see, is not parallel to the bottom plate, subtends an angle theta with the horizontal. The height, the gap in between the two at x equals 0 is provided as HL, and the distance between the distance between the two at x equals L is also provided, and the density and rho, the density and the viscosities are constant. So this H, the separation between the two plates, is a function of x. We would like to find out like what is going to be the flow rate, etc., for such a situation. So let's read the problem, and I would try to explain any other terms that appear over here. So lubrication force flows are characterized by incompressible fluids, and there are some applications, some examples which were provided. Layer of water between the ice skate and the ice, the oil that lubricates the moving parts of an internal combustion engine, etc. So, uh, in any situation, because most of the time the viscosities of these liquids are rather high, and the flow is not due to a pressure gradient, but the flow is due to the movement of one of the parts. For example, the movement of the ice skate, movement of the skate on the ice. So the velocities are small, and therefore the inertial terms are insignificant compared to the diffusive terms. Now we know what's the implication of that. That means the entire left-hand side of Navier-Stokes equation, which denotes the convective transport of momentum, can be neglected, and we will be left with only the diffusive terms. And the flow can be treated as two-dimensional, and there is obviously the system size is small, and therefore the body force, whatever be the body force, will have a very small effect. Now, and then the problem is defined over here. This is moving with a constant velocity u naught, and we can assume that there is a constant volumetric flow rate of V of the lubricant in the system as a result of the motion of the plate and the applied pressure gradient. If we apply a pressure gradient, though we have shown here in the figure that P equals 0 in both cases, but we can also have a pressure gradient imposed on a system, which would be the most general form. And then if for some specific applications, when there is no pressure gradient, you can simply set that term to be equal to 0. So we need to solve the governing equation. We need to find out what are the boundary conditions, and we have to, again as before, obtain an expression for dpdx and the local pressure in terms of the local height between the two plates, the velocity of the bottom plate, and the volumetric flow rate. So we need to find finally the volumetric flow rate and the load that the bearing can support. So that's very important. We have solved one such problem in our previous class. So if once we have the pressure difference evaluated, then that can be transformed into the pressure, the force that can be supported by the top plate in terms of all these system parameters. This is essentially a problem which I will leave for you. Uh, it's the same as we have discussed in the first problem. We realize that the pressure difference, if any, it's going to vary with x. It does not vary with y, as the gap is small. So we realize that the pressure is a function of x. And then we write the Navier-Stokes equation. So maybe I can write the steps. So the first part is identify pressure is a function of x only. The second is write the Navier-Stokes equation. And from the Navier-Stokes equation, you can cancel the left-hand side. This would give you a relation between dp dx, and I'm writing dp dx to underscore that I have identified pressure to be a function of x only, which automatically arises due to the small gap in between the two plates. And then I am going to have the right hand side. It is simply going to be d2 u by dx square plus d2u by dy square. And we realize that can you make some approximation in here to solve this, to simplify this equation any further? Any opinion from your side? if I look at the left hand side and the right hand side, do you feel that there is some term or terms, one term or terms, which will rather be small as compared to the other term? Am I audible?
The D2U DX2.
D2U dx2 is going to be small in comparison to what we have for this case. And what's the basis of your statement? Why do you
Y is rather small.
why the gap is very small as compared to the length of the plate? So of course U varies strongly with Y in comparison to X. So therefore I drop this term and I simply have uh, I simply have dpdx to be equal to mu times d2y by dy square. So I can integrate this equation. Integrate this equation, and then what I would get is an expression for U, and U is going to be a function of this. I wouldn't write completely. You would see that this is going to be a function of U naught. It is going to be a function of dp dx, the imposed pressure gradient. It is also going to contain H, which is a function of X, and obviously this U is a function is going to be a function of Y. So you should be able to write this, obtain this expression for U. Once you so the in the entire exercise that we have done so far, there is one part which is involved, the understanding part which is involved, where we can approximate the flow to be one dimensional. The U changes only with X, or rather U changes with Y more significantly as compared to the variation of U with respect to X. Once we do that, then this integration can be obtained, and the next step would be V, where V is the volumetric flow rate, would simply be equals to the V is the volumetric flow rate per unit depth, so 0 to Hx, and we would be able to substitute the expression for U we would be able to substitute the expression for U from here, and then we would be able to obtain V as a function of U naught Hx dp dx and the property which is going to be equal to mu. So this is how you can obtain an expression for V. And with this, then I would assume that you would be able to find out what is going to be the final form of pressure. So pressure, of course, here is going to be function of X. So evaluate P as a function of X. And once and we would also assume that H varies linearly, like the last problem. So H varies linearly with respect to X. So from this, you would be able to obtain what is Px. And once you have the Px, then the load that it can support is simply going to be P of X multiplied by cos theta. If you remember, I have the bottom plate and the top plate. This angle is theta. So P, which is a function of X, so I have Px over here. So Px multiplied by cos theta into dx, and this of course is from 0 to L. So I would give you the final expression for the load, and the rest you have to do it on your own. The answer to this is 6 pi U naught So, so this would be the final form. And once again, I try to impress upon you is that this problem is fundamentally the same as the previous problem. There's not much of a difference between what we have done for the tapered tube, the considerations that we have used for the tapered tube, and the one that we have over here. So this gives you an idea of the load that it can support. And from the expression, it is clear that the load bearing capacity, which the left hand side increases with increased flow rate. So it is definitely going to increase with the increased flow rate. It increases as the two surfaces become more parallel to each other, and it increases as the gap width increases. So I would leave this. I would advise that you do this problem on your own. The rest of it based on whatever we have discussed in here. Okay. Uh, Half an hour. So we have half an hour more to talk about some other interesting problem. Now, some of you have heard about cell sorting, which is a very common practice in separation of cells based on their size, based on what type of cells they are, and all. So it's a size-based separation in which cells are made to flow through a tube. And of course, the density of the liquid, the carrier liquid, is chosen in such a way that cells will start to settle as they move with the fluid in the tube. So it looks something like this. So the cells are going to settle, but at the same time, as they're settling, the x component of velocity is going to take that cell away, and it's finally going to be deposited at some point. So the where they are going to get deposited would depend on the density difference between the cells and the liquid, but more importantly on the size. So if you have two different types of cells, or maybe multiple cells of multiple size, then some of them are going to deposit on the walls of the tube. The rest are going to simply carried away with the liquid. So by choosing the liquid and by controlling the flow rate, it would be possible for you to separate the cells based on their size. So that's how the cell separation or cell fractionation system do work, does work. So let's read the description. Cells are injected at the center of the tube. The radius is R, and it is carried by the fluid, and the flow rate you can fix. Obviously, the flow rate you can fix over here. And the denser cells, they will fall quickly under the action of gravity, adhere to the tube wall, and hence do not pass out of the tube. So what we need to do is we need to find out what is the length. How do you predict the length that a cell of a specific density will take before it settles on the sidewalls of the tube? So for that, we would assume that the concentration of the cell is low, such that it would not disturb the laminar flow in the cell significantly. We'll also assume, which is a big assumption because the cells are generally not spherical, but in order to solve this problem and in order to get some idea of what would be the expression for such systems, of separation in such systems, we'll assume the cells to be spherical. The radius is known, which you can find out from experiments, from microscopic observation, and the density is rho plus delta rho. So delta rho is the additional density that the cells have in comparison to the density of the flowing fluid. So what we need to find out is the length that a cell travels before it hits the bottom wall. Okay, so you can choose the length of this tube such that some of the cells will be carried away, some of the cells will be deposited on the surface, which can then be collected, and therefore cell separation can be achieved. We have to use certain physical principles, facts that in fully developed flow, in presence of gravity, the pressure distribution in the vertical distance is hydrostatic. So over here, the distance in the variation of pressure in the r direction is simply going to be hydrostatic. And the actual velocity profile, since it's laminar, it's going to be parabolic. We have to assume that the cell is spherical, that we have already discussed. It reaches its terminal velocity. This is very important. The moment you release the cells, it will start to fall and be carried away in the direction of the flow. But we have to assume that it will instantly reach its terminal velocity. So its downward component velocity, the downward component of the velocity, if the cells are released in a stagnant stream, stagnant liquid, then it will reach the terminal velocity in no time. So that's a big assumption that we are making over here. So the cell is reaching its terminal velocity immediately after injection into the tube. The injection is already always done at the central line, and it gets carried actually at the local fluid velocity of the tube. So once it starts falling, if it's at this point, then it's going to have a z component which is equal to the velocity of the fluid at that point. And of course, as I move towards the bottom, the velocity is going to progressively decrease, and it's the x component or z component of the velocity would rather be small. So at any point, the cell is going to have a vertically downward component of velocity and a horizontal component of velocity. The horizontal component of velocity keep on changing as we move as we move towards the tube wall. Is the statement of the problem clear to you? Any question that you have?
So could you please clarify what exactly L denotes? Like where does it start from? The
Okay,
point
it's
shown here seems to be
yes,
a bit random.
right. It can start at any point. Okay, you can have this point over here as well, but let's say once the flow has become fully developed, in fact I should have, so that's the tube. The flow takes place through the tube, and it would require some length. As you all know, the entrance length, let's call is L entrance, for it to become fully developed. So the profile is simply going to be like a parabola from that point onwards. You can inject the cell at any point beyond this distance. Now, where you inject this will govern what is how, and this you can, sorry, let me rephrase it. I'm injecting the cell over here, and I am going to calculate what this L going to be. So depending on how much of remaining length I have, I can choose to have the cells injected at any axial point in between. Am I clear now?
Yes, sir. So the cells are injected vertically, like from the top or from the bottom.
I wouldn't say vertically. The generally the arrangement would look something like this. In a cell separator, the cells are released from a feeder at a very small rate, and so initially they get exposed to the moving fluid, and immediately because of the density difference they would start to move towards the bottom. As they move towards the bottom, they are getting carried away in the z direction. So I wouldn't say it's vertically. They are theoretic. In order to solve the problem theoretically, you will assume that the cells appear without any velocity of their own when they get discharged from the nozzle that supplies or that feeds the cells into the flowing fluid. So the moment if they come out of the feeder tube, then they will immediately have the terminal velocity, and will attain the same z component of velocity as that of the fluid with which it is in contact. Am I
Yes, sir,
clear?
understood. Thank
Okay,
you, sir.
sure. So my aim here is to find out this L in terms of the system parameters. Okay. Uh, so we have to find the distance L, and of course, once the cell is falling, can you tell me what are the forces which are acting on it? What could be the forces which are acting on the cell that has started its journey towards the bottom of the tube? Anyone? Just identify one or two.
Body force and buoyancy force.
Body force and buoyancy force. Can there be any other force? Body and buoyancy are obvious. So it travels towards the bottom, and there is a buoyant force which is acting in the opposite direction. So there is a net.
Viscous force.
Uh, would you give a more fancy name to it? You are right. You have identified the.
Viscous drag.
That's drag force. So you have, and the genesis of the drag force is, as you have mentioned, viscosity. So it's a viscous force, but in order to highlight the effect of the reduction in motion, reduction in velocity, drag is more commonly used than viscous force, because viscous force is also used to denote the right hand side of Navier-Stokes equation, if you recall that. So I would rather separate the drag force from the viscous force, but you are correct in identifying that viscosity is the prime cause for the drag force. So there are three forces which are acting. One is the gravity force, the other is the buoyancy force, and the third is the drag force. Uh, is there any relation between the three? The gravity, the buoyancy, and the drag?
Yes, sir, through Stokes' law for spherical particles.
Okay, through Stokes' law of spherical particles, I can express what is going to be the drag force. That is like 6 pi mu radius times velocity. So that is what the drag force expression, which is the Stokes law. But my question is there any relation between the three forces, the gravity, the buoyancy, and the drag?
Their sum should be 0.
Their algebraic sum should be 0, right? Because we have assumed that the cell has reached its terminal velocity, and since it has reached its terminal velocity, there is no net force acting on it. So in order for it to not have any force acting on it, the algebraic sum of these three should be equal to 0. Or if we imagine the cell which is falling downward, then the gravity force must be exactly balanced by the buoyant force and the drag force. The drag and the buoyancy would like to prevent the motion of the cell towards the bottom, whereas the gravity pulls the cell towards the bottom, and therefore at equilibrium at equilibrium, that means at terminal velocity, these three should be the same. So I write the expression for gravity force. I write the expression for the buoyant force. I have typed these expressions, so there could be some mistakes in there. Just check if I have done it correctly later on. And drag force, as you have pointed out, it's simply going to be equal to the Stokes law. But I would like to highlight this is the subscript of V in here. Why did I say this? That these two are straightforward, gravity and buoyancy. But when I write FD, I bring to your notice that what is the velocity that I need to use in this? What velocity should I use? Is it the velocity of the fluid?
Terminal velocity.
Terminal velocity, and it's the velocity in the art direction. Velocity in the increasing art direction that I need to use, not the local velocity, which is principally in the z direction. Okay, so that is something which we need to keep in mind. And that's what I wrote, that the cell is moving with a velocity Vr in the R direction. And as we have identified that the equality would give me an expression for the velocity with which the cells are falling in the fluid. Fine. And so far in our analysis, what we have written, what we have shown in this page, there is no mention of any flowing fluid. Okay, so we did not say anything about the flowing fluid. There is no effect of that. It's only the gravity, buoyancy, and the drag forces which are connected to each other by this expression. Whenever you have a question, you let me know. Now, if I would like to find out what's the radial location as a function of time. So the radial location as a function of time would simply be equal to whatever be the velocity, and from 0 to t in unit time t, how much, what is the distance that it has traversed, the downward moving particle has traversed. So this is the expression for the this is the expression for the radial location. And we understand that for it to settle at the bottom, this R is simply going to be equal to capital R. Okay, so the settling time can be calculated by simply equating this R as capital R, where capital R is the radius of the tube. So of course we can write what is the time that the cell will hit the wall. So this simply follows from the expression that we have above. Now, why did I calculate the time t? Can you tell me what is the reason that I have calculated the time t?
The cell will move forward only for this amount of time.
Exactly. The cell will move, and the so-called distance L that we have written, the so-called distance L that we have in here, the time is, we have to find out how much of what is going to be the value of L for this time tr. Okay, the horizontal component of the velocity that we need to figure out. Now, the x direction velocity, or z, doesn't matter. I wrote x. This is the parabolic expression. From this parabolic expression, you can find out what is the average velocity. This is the flow rate, and so therefore the relation between the flow rate and delta P, you know about this expression. You have seen this expression before. That's in fact probably the second problem in fluid mechanics which we have solved, the parabolic velocity profile for this case. But we have to keep in mind about this time and bring this time somehow in here. So the Vx is going to be a function of R, and this R is changing with time. So therefore, what is the length is simply going to be Vxtt from 0 to the time it takes for the cell to reach at the bottom. So when you do this exercise, it's a slightly bit, cumbersome in terms of algebra, but conceptually there's nothing in here. Is you would be able to find out what is the length that this cell would traverse before it reaches the bottom. And when you substitute the expression of t, etc., you can have a compact expression of the length that you should provide for settling of a cell of diameter A, which where the density difference between the chosen liquid and the cell is delta rho. And we can take this mu to be the mu of the liquid, and this we can do since we have assumed that the number of cells do not alter either the flow pattern or the property of the fluid in any meaningful way. So mu is going to be the density of the fluid. A is that of the diameter of the cell. Delta rho is the density difference, or rather the incremental increment in density, and R is the tube through which it is flowing. So most of the cell separation units that are in use, they employ this principle, this sort of a thumb rule expression to find out how much of length is to be provided, or if the length is fixed, then what kind of a flow rate is to be maintained in order to have the separation within the provided length. Do you have any question? Okay, so this is another example of the use of our transport phenomena in different problems. So these are quite interesting problems if you think of it. And what we have done is we have started from the first principles. We have used just the basic Stokes law, the buoyant force, and so on. And we used Navier-Stokes equation. We used the Hagen-Poiseuille formulation and the parabolic distribution. And from that, an elegant expression can be obtained. So that's one of the beauties of studying, modeling a flow process in such cases. The last problem, once again, I would discuss and not solve, provide you with the answer and then the solution at a later date. This example I have taken from biology. So we have this is quite common where there is one basic epithelium is a basic type of animal tissue which forms the cavities and surfaces of structures throughout our body. So they do not contain any blood vessels and they are permeable to the flow of nutrients and oxygen through them to the mass that lies above it or outside of it. So this is an extremely important. The epithelial tissues are extremely important for transport of drugs. So you have a body fluid, it could be blood that is flowing, and you have injected some drug into your body through the bloodstream, and you'd like to see that how much of blood, how much of uptake of this medicine is going to be taken up because of this process, because of the diffusion, or rather the permeation. I wouldn't say diffusion, because diffusion only limits our example to diffusive transport. Permeation is probably the right term, where there is a possibility of convection as well. So this permeation of the drug is to be calculated based on this, whatever be the initial flow rate that you have, and there is going to be some leakage from the bottom and from the top. Let's call it as Q. And this Q would obviously depend on what's the pore size of the epithelial tissue, what's the size of the drug molecule, and how much of a pressure gradient you are creating in between, in at the inside and at the outside. What is the pressure difference in between the two? And we would also understand that as Q naught starts to flow and as we lose some of the material through the pores of the epithelial tissue, this Q, the volumetric flow rate, is going to be a function of X, which is going to be intimately related to the Q, that the small q that we have over here. So an apparatus has been built for testing the effect of various drugs on the rate at which an epithelium can pump the fluid from its luminal side, that means the side facing the fluid, to the side which lies on the channel wall. The cell lines in the top and bottom surface of a flow channel has a separation of H, so it's just a description of the one that we have. And the length is known, the depth into the page is W, so it's a rectangular system where all your calculations could be based on per unit depth, or you could simply multiply that by W in order to obtain the total amount. Each of these walls is porous, so that any fluid pumped by the cells can leave the channel. So anything that the cells take up is going to be rejected on the other side. The rate is provided as Q per unit area. It could be mass or it could be volume, doesn't matter. It's Q per unit area of the channel and Q has the units of length per unit time. So Q is the volume per unit area per unit time. So obviously Q then will have the units as length per unit time. And like any any channels or any channels in our body, we can always say that the height of the channel is much less than its length. So H is much less than as compared to L. Is the problem statement clear to all of you? The only thing is Q varies with X. Small q is the uptake, or rather the leakage flow rate, so to say, and H is quite small in comparison to the length of the channel. Okay, I go to the next part of this. The fluid enters the channel at the left with the flow rate Q naught. The pressure is provided, and since it's a gauge pressure, then we know that we do not have to do anything else. We can directly use P naught. You probably remember that from Bernoulli's equation, we always use the gauge pressure and not the absolute pressure. The first part, to determine the rate at which the cells are pumping fluid out of the channel is instrumented with pressure transducers that can measure px. So the factor that you can control is Q naught, and as a result of changing Q naught, the pressure inside the channel will change. The pressure variation inside the channel will change, and you can measure what is px. What's the value of px at different points? Now you may not be able to simply use a linear variation, because you also have leakage at the same time. So we need to find out what is the pressure distribution if Q equals 0, and we know what would that be. If Q equals 0, then it's simply going to be the linear distribution. And what is the pressure distribution for Q not equals 0? When I have suction, when I have leakage out of this, then it's also provided that the P at the end is P sub E. So we have to find out what is Q. Because your aim, the purpose of your experimentation is to find out how much these epithelial cells can transport the liquid and the drug along with it to the other side. So through instrumentation, I know what is PE, I know what is P naught. So I need to find out what is the rate at which the leakage rate. And find the last is we need to identify the criteria necessary for our assumption that we need to solve the problem is that the viscous flow is going to dominate. And the answers must be in terms of the known quantities. So L, W, H, Q naught, P naught, PE, rho, and mu. Okay, and of course, for all the answers, not all of these are going to be needed. Is the problem statement clear to all of you? So I wouldn't solve the right. I wouldn't solve the problem. Rather, I would give the pointer to each of these. For example, A, B, C, D. I have written them on separate pages, and I would give you some idea of this. So if Q equals 0, so since Q equals 0, this would simply give rise to dp dx to be a constant. Or the rather, I would say it's a linear variation for this. But if Q is not equal to 0, then dp dx is not going to be equal to a constant. This is the first thing that we identify from our problem. So for this case, I can write the Navier-Stokes equation as mu d2vx by dy square, because the velocity varies with y, minus dp dx. That's the imposed pressure gradient in the system to be equal to 0. I would be able to solve this in order to obtain what is Vx. Okay, and the boundary conditions what are the boundary conditions to be used in this case? Can anyone answer this? The boundary conditions to be used.
No slip.
No slip at the top and at the bottom. So y equals 0 and at h my Vx is going to be equal to 0. So this will give me a compact expression for Vx, and from the expression for Vx I would be able to obtain what is the average value of what is the average value of the velocity in terms of as a function of obviously dp dx, and there would be the h, and there would also be equal to mu. This we know very well, and from here I would be able to obtain what is q naught, and we understand that for this case q naught will remain unchanged as my q is equal to 0. So I would be able to obtain q is simply going to be the area multiplied by the average velocity, and therefore at the end I would get an expression for dp dx in terms of q naught, in terms of mu and w, h, etc. Once I integrate this equation with the known pressure, then it would simply, I'll give you the, I don't know why this, my pressure for a system in which there is no leakage is going to be the familiar no slip condition, sorry, familiar linear variation with x that we have for the pressure. So these are the steps which are straightforward. So I think you probably do not have any question on this, but if you do, please let me know. So this is the usual case that we have done so many times. If there are no questions, then I move to the second case where q is not equal to 0. So what you have is if I draw a small section of the channel, you have q naught in here, you have q, small q, that are going out of this, and what I have then is q, which is therefore a function of x, and this q function of x can simply be written as the starting value minus 2qwx. So y2, I mean 2 essentially denotes that you have from the top as well as from the bottom. Now the governing equation I have then is dp dx from the Navier-Stokes equation as mu this is the Navier-Stokes equation. Previously, I did not have to worry about the first term, as there was the Vx did not vary with x. So we simply assume that it's a fully developed flow, and therefore this part is going to be 0. My dp dx is simply equal to d2Vx by dy square, and then I proceeded to integrate this. Now here comes an assumption. Can we make some assumption in here which would make our life a bit easier by dropping the first term? Is
Reduce the distance between the plates. I mean the height. Reduce the height small.
Okay, that is one way. What you but even then, I all right. I keep accept it, and I am still looking for some other opinions, some other ideas. Is there any other option available to me which would allow me to drop the first term? Tell me, why would Vx change with x? What is happening that Vx is going to be different at different values of x? If I, okay, someone was about to say something
Flow
probably.
rate is changing in x direction, so
Flow rate
that's
is
why.
changing. Flow rate is changing in the x direction, so that's why my Vx is going to be a function of x. Okay. Now you tell me the possible assumption which you can mm, employ in order to make the first term small in comparison to the last term. What has to happen so that I can, as an assumption, approximation, I can drop the first term?
Leakage rate can be small.
Leakage rate can be small. So there are two ways by which I can handle this problem. One is I can make the two plates very close to each other. But even then, if the suction rate is high, then even for plates being very close to each other, had they been solid plates, then I could have reduced the distance between the two and would safely say that Vx, the variation of Vx with y will definitely predominate over Vx, the variation of Vx over with x. But these are not solid plates. These are porous plates. So the rate at which the fluid leaves the system will play a more prominent role in ensuring that the variation of Vx with x is rather small. And it can only happen if this q is small. This q is small in comparison with this with the total flow rate. Okay. So if that's the case, if small q is small, in that case I can say that this is going to be large in comparison to this if q is small, and then it my dpdx will be equals as previously minus 12 mu qx. This is what you have done in the what I have done in the previous slide by whq. The only difference here is that my q is a function of x, and this has to come from here. So I can substitute the expression for q, which is a function of x, from the conservation equation that I have written over here, and then substitute it, integrate to find out what is going to be my pressure, and the answer to that is going to be minus 12 mu x by wh cube q naught minus q wx. And you can clearly see that if I set q equals 0, then it reverts to the original expression that we have for pressure. So the problem is when you make the right assumptions and when you identify the conservation one and the assumption over here, it simply boils down to it becomes a rather simple problem. Given that px equals pe, you have to find q. This I will leave since we already have the expression for p. The expression for this is simply going to be from the previous slide. So this is what you would get from the previous case. This part I would like to spend some time, in fact 5 minutes, to find the criteria necessary for the assumption that the viscous flow dominates is to be valid. So if you recall that in developing this equation, what we have done is we have simply said that the left hand side of the Navier-Stokes equation, which denotes convection, can simply be neglected, and the right hand side, which is essentially the viscous forces, that is going to be prominent. That is going to be that will predominate. So how far this approximation is valid? So mathematically, what we said is the left-hand side of the Navier-Stokes equation, which is Vx del x plus Vy. Oh, so what we this must be quite small, and if so, the numerator is essentially the convective flow, and momentum transfer due to convection. The denominator is the momentum transfer due to diffusion, and only when these two ratios are quite small, with respect to 1, you'd be able to say that this is going to be 0. So you need to apply your order of magnitude analysis to each of these terms and see what this will result. For example, the first one, del Vx by del x, can be written as it is going to be of the or it's going to be of the order of d dx of q, which is the flow rate, divided by a. It is of the order of, I am not saying it's equal to, and so therefore this is going to be 1 by wr, where a is w times r, and this is going to be d dx of, and we know q is simply equals q naught minus 2 qwx. So that is going to be 1. On the other hand, this Vy can be simply be equal to Q, where Q is the suction rate. So with this kind of approximations, once you put in, you would see the final result would look something like Vx times Q by H plus Q times Vx by H. These are order of magnitudes only. Do not write them, do not say that they're equal. And this is going to be mu times Vx by H square. They should be very, very small in comparison to 1. You can simplify this. You can get the answer. Do not look at this expression right now. Tell me, what do you think the result would be? When my assumption that the viscous flow dominates is valid? You can substitute Vx del x, Vy del Vx del y. Vy is simply equals Q. So similarly, you can write del square Vx del x square, del square Vx del y square. I can even neglect this del square Vx by del x square. based on our assumption as before, and we get an expression like this. But intuitively, can you tell me when my assumption is going to be valid?
When h is very small.
When?
H is very small.
Fine. When h is very small. Anything else that would be small? Think about the problem once again. I have a flow which is large q. I have a flow which is small q. So when x is small, I completely agree with you. Uh, is there anything else? Uh, Anything else that needs to be small? Smaller?
Capital Q as well.
Capital Q is large or capital Q is small, or small q is large or small q is small, or rather the small q is rather lesser in magnitude. See, what is the viscous flow dominates to be valid? For viscous flow to be valid, you want the disturbances present in the system to be small. So if you look at what I have drawn over here, what is the cause for perturbation in the straight flow, straight parabolic flow? Do you identify any perturbation that I am providing in here?
Small q.
Small q. So the small q has to be small in order for the assumption that viscous flow is going to dominate, to dominate. Is there any physical property which would tell you that when viscous flow is going to dominate?
The
Any
viscosity will be high.
viscosity. So viscosity has to be high. We know that in viscosity should bring order to the system. And what brings disorder, apart from the Q that we have imposed, what brings disorder is the inertial force term. So inertia brings in disorder, viscosity brings in order. So if it is inertia, then which physical property is related to inertia?
Rho.
Rho, the density, because inertia is simply related to mass, and the corresponding property has to be equal to rho. So rho has to be small such that the inertial force is small. Mu has to be more such that the viscous forces would be equal to more. The leakage rate is going to be small, and the separation between the two plates, as one of you pointed out at the beginning itself, the separation, which is h, needs to be small. So once I have rho, h, mu, and q, and I bring to your, I again emphasize that Q has units of meter cube per meter square per second. So Q has units of meter per second. So if I have rho h, which is a length scale, mu, which is viscosity, and small q, which has units of meter per second, then what am I defining as the term, the combination which has to be smaller in order for the assumption to be valid? What comes
Reynolds
to,
number.
right? And what kind of a Reynolds number is it? Is it the flow Reynolds number which is related to capital Q, or is it some sort of a Reynolds number which is related to small q? Which Reynolds number are we talking about here?
Say related to small q.
Related to small q. So the analysis of this would provide you, when you do this, and I leave that to you, is that rho small q h by mu has to be small. So the uh, leakage uh, uh, leakage flow rate, rather the effective Reynolds number characterizing the leakage flow has to be small. And you can clearly see that what I said so far is rho has to be small, inertial force less, mu has to be large, viscous force to predominate, q has to be small such that the perturbation is small, and h has to be small such that the viscous force, I mean the flow in the variation of flow in the x direction is rather small in comparison to the variation of the flow in the y direction. So altogether, what we see is some sort of a leakage Reynolds number has to be small. And interestingly, it says nothing about capital Q. So the assumption what we have started with, the viscous flow dominates. It depends more on small q and rather less on large q. So much of understanding can simply be obtained by putting the terms, the order of magnitude, and do an analysis and come up with an elegant solution to the problem. I'll share the solution after about a week, not now. I will leave this to you, leave this for you to figure it out and get the final form. All right. So, any question for this up to this?
Sir, in this question, are we basically trying to keep the system in laminar zone?
We have to keep it in laminar zone because the form of the Navier-Stokes equation that we have used is valid only for laminar flow. The moment we bring in turbulence in the system, then the momentum transfer is not going to be because due to viscous transport, it's going to be due to the fluctuating component of the Navier-Stokes, fluctuating component of the velocities. Did I talk about this in the fluid mechanics class? The fluctuating components of velocity in turbulent flow, how do they add or how do they contribute to the overall transport of momentum? Did I explain the concept of Reynolds stress? Probably not. Your silence tells me that I probably haven't done that. So I will discuss about it in a separate class, but in fact, Professor Manish Kaushal will probably talk more about Reynolds stresses. I will talk to him and see whether he or I should tell you about the turbulent flow and the fluctuating component, time fluctuation of the velocity, and how the time fluctuation contributes to additional stresses. But that's a separate one. Here, in order for me to use this form of the Navier-Stokes equation, I need to keep that in laminar flow only. So to answer your question in one sentence, we are imposing laminar flow in the system. Our analysis is not valid for a system where we have turbulence. Okay, any other questions? Fine. So I'll have a break and then we'll come back and discuss more about it. And I will upload this in the module probably by today itself. So a break for a few minutes then. Okay, let's start again. Am I audible? Can you hear me? And can you see the slide?
Yes, sir.
Okay. So I'm going to start something new in the remaining 25 minutes. Uh, mm, this concept is probably one of the most interesting in chemical engineering as well as in mechanical and aerospace engineering. It is the concept of boundary layer. We have had some discussion on the boundary layer before, and I'm sure you had the same discussion for heat transfer as well. So we understand that everything happens in a very thin layer close to the interface between a solid and a fluid. So if we talk about the transport of momentum, the transport of energy, or if it's a case of a dissolution, for example, if there is a salt slab and there's a water flowing on top of it, then the salt gets dissolved and the concentration of the salt changes sharply near the interface and within a thin layer, and beyond that point, the concentration remains constant. So the from ancient time, people have understood that the need for defining a region close to a solid surface, which would let them allow uh, evaluate important properties related to motion. For example, the first concept of boundary layer was proposed by Prandtl, and it provided the missing link between the experimental results and the theoretical understanding of that time. So the Euler's equation, which uh, which uh, which assumes that there is nothing like viscosity, no viscosity of the fluid. So in order for it was providing results, it was giving results that in order for the liquid to move from one point to the other, it do not need to provide any pressure gradient. The anomaly became even more prominent while designing the ships. The drag force, they knew at that time that there is something called drag force, but the solution or the evaluation of the drag force was almost impossible to achieve because the complete solution of Navier-Stokes equation in such a large flow domain was impossible. So then came Prandtl and he revolutionized by simply assuming that everything takes place within a layer very close to the surface. All the momentum transfer, drag, etc. are caused by the thin layer, viscous layer, in which the viscous forces are important. So if you think about this layer, it is greatly exaggerated. The thicknesses are of the order of millimeters to centimeters at the most for very long, very long surfaces. So the viscous forces are important inside the thin boundary layer, and outside of this boundary layer, the flow can be treated as invisible, as if there is no viscosity. So Navier-Stokes equation will have to be solved in a region very close to the surface. Outside of this region, Euler's equation is more than sufficient. So this has resulted in a revolutionary progress of aerodynamics, and similar such processes which would lead to designing of ships, designing of efficient cars and other objects with very low drag. So all the fancy designs that you see in racing cars are based on our understanding of how the boundary layer develops, what is going to be the pressure distribution inside a boundary layer. Can we disturb the boundary layer in such a way at a point near the end of the plate? If you consider this blue one as the side of a car, so what is going to happen? The formation of wakes, formation of low pressure regions at the back of the car, and how do I break those wakes so as to create a smaller region having low pressure. So if you have low pressure at this point and high pressure at over here, because of the formation of the wakes formation of the boundary layer, for the detachment of the boundary layers from the surface, which causes the wakes. So this produces a force which is the force required to move it in the in towards the left with certain velocity. So the spoilers that you see in the car are a direct result of our understanding of how wakes formed and how to break the wakes so as to reduce the unfavorable pressure gradient which is formed due to the high speed motion of the car through the atmosphere, and how that lead to the reduction in the drag coefficient. There are many examples of boundary layers just in momentum transfer alone. So the movement of the golf balls, when you strike a golf ball, you have seen that the golf balls had dimples on them. They have dimples on them, and if you hit a smooth ball with the same force, same direction, and a golf ball which is not smooth, which has dimples on it, the golf ball will travel further. This is because of the formation of the turbulent boundary layer from the very beginning, because of the dimples that reduces drag. So from the design of a ship, of a car, of a plane, of a space shuttle, everything is related to boundary layers. The amount of heat generated when a bullet travels through the air due to viscous dissipation, which is something similar to solid friction, can also be attributed to the transport processes which are taking place inside the thin boundary layer. So the combined study of heat, mass, and momentum transfer together has its origin in the understanding of the boundary layer. So in chemical engineering, we cannot live without a complete and proper understanding of the flow processes inside a boundary layer. And from now, we are going to spend quite some time on this. But let's think about some of the basic definitions of a boundary layer. So we have an uniform flow V, which is not a function of y. So this is a constant velocity flow that is approaching a solid plate, which is stationary. So the moment the fluid layer hits the solid, due to no slip condition, the velocity will be brought to zero at this point. The interaction between the liquid and the solid will slowly propagate through the fluid layer, and as we move away from the fluid layer, the interaction which is due to the viscous forces will slowly die down and will come to a point where the velocity, which has started from a zero velocity and progressively increases as we move away from the boundary layer, reaches almost like the free stream velocity. So if we move outside far from the plate, then this velocity is known as the free stream velocity. So the term free probably refers to that it is free from viscous forces which are present inside the boundary layer. So boundary layer is something like like a conceptual imaginary thin layer inside which the velocity is going to be a function of x and y. So it is going to be a function of x as well as function of y, whereas the velocity, the approach velocity, if you see over here, it's a constant, not a function of x or y. Now, what is the relation between approach and the free stream velocity? Are they equal? If you have flow over a flat plate, and if this side is infinite, I mean, if you have a large body of air in contact with the solid plate, then V and U infinity are going to be equal. So V equals U infinity for flow over a flat plate, and for any and U infinity is going to be a constant. U infinity is not going to be a function of x. But if it's a curved plate, then the V and U infinity would be different, because you have lesser flow area for the flow to take place, and that U infinity for a curved plate can be a function of x. So U infinity is definitely not a function of y. For flat plates, U infinity is not a function of x as well, and for a flat plate, U infinity is equal to v. Whereas for a curved plate, U infinity will still not be a function of y, but it could be a function, maybe a weak function of x as well. So that's the definition of approach velocity, free stream velocity, and so on. And the imaginary layer inside which the viscous forces are important is called the boundary layer, and its thickness is generally denoted by the sign delta. Okay, so by looking at the velocity profile, you can see that the velocity approaches the free stream velocity asymptotically. So it's difficult to pinpoint where the velocity is going to be exactly equal to U infinity. So in order to address this problem of accurately defining the boundary layer, it has been commonly accepted that when Vx reaches 99% of the free stream velocity, we say that we have reached the edge of the boundary layer, and that thickness is is denoted by delta. So what I have written here, I have already explained that the inside the boundary layer, the flow is two-dimensional. The flow depends on both x and y. It is the viscous forces are important, and outside the boundary layer, the flow is one-dimensional. The flow could also be a constant, depending on whether you have a curved plate or a flat plate, and Vx is equal to U infinity, and whether U infinity is equal to V, that depends on the shape of the plate, and delta is the boundary layer thickness. Is there any question so far? Okay, so even with this definition of boundary layer, we have some problem, because the nature of the velocity variation that you see over here is asymptotic. So if I tell you to measure the velocity profile, if two students are measuring the velocity profile using some sort of a very accurate pitot tube, now you can say that your measurements can say that the velocity reaches 99% at this point. Other persons can say that the velocity reaches 99% at this point. So the thickness determination, evaluation of the boundary layer thickness by experimentally is prone to significant errors because of the nature of the variation of the velocity. So we require some other definitions which are more correct, which are less prone to the uncertainties associated with the measurement of velocity using any instrument that you can think of. So the impetus for such a for evolving such a definition comes from the nature of the velocity variation. It is again something which I have already discussed. So I will leave this. Only the left hand side top part I would like to discuss some for a few minutes. So in the upstream, the velocities are fixed, velocities are constant, which is the approach velocity. And over here, I have an airfoil, and therefore, when the velocity, when the stream strikes it, there's going to be some sort of a stagnation point. So stagnation point is the one where all the kinetic energy is going to be transformed, is going to be brought to a halt, and the change in kinetic energy from some value to zero will manifest itself by a change in pressure, by an increase in pressure, which is known as the stagnation point and stagnation pressure. And then the velocity, the laminar boundary layer, will start to develop all along the airfoil. Beyond a certain distance, the perturbations are going to be prominent in the boundary layer. There's going to be some sort of disturbances which you could see, and the turbulent boundary layer will form. So initially the boundary layer is going to be laminar, then it's going to be turbulent, and a point would come where the turbulent boundary layer can leave the surface and form recirculatory patterns which are commonly known as the viscous wakes. So viscous wakes, as I have mentioned, are low pressure regions. If you have low pressure over here and high pressure over here, so the natural tendency would be if the airfoil is moving, the natural tendency would be a reverse pressure gradient would apply on this. And so it is of our interest to reduce the drag, to break this viscous wakes into smaller wakes, and to create a condition in which we can have a lesser amount of this drag. And when we talk about drag, there are two types of drag. One is the one which is parallel to the direction of flow, which is known as friction drag. And there is going to be another component which lifts the airfoil, as we already know. So there could be a lift force and the friction drag. So we will talk about the friction drag more into this in this course. But let's come back to our previous discussion, that how difficult it is to pinpoint the location where the velocity reaches 99% of the free stream velocity, and this would require some additional understanding. And this part I am teaching mostly from Fox and McDonald. Okay. Then comes the some considerations. Flow inside the boundary layer. In absence of any pressure gradient or any body force, this is the Navier-Stokes equation that you already know. Now in here there are certain assumptions that one can make, which are commonly known as the boundary layer approximations. So the actual velocity is going to be very large in comparison to the velocity in the perpendicular direction. The del Vx del y is going to be large as compared to del Vx del x, which is obvious because the thickness of the boundary layer, this y is small in comparison to the length scale over the length over which the flow is taking place. So I can make this as my this is an approximation which is acceptable. And del square Vx by del y square, for obvious reasons, is going to be much more quite large as compared to del square Vx by del x square. So these three are collectively known as the boundary layer boundary layer approximation. So I'm going to write that Vx is going to be large in comparison to Vy, and del Vx del x is going to be small in relation to in comparison to del Vx del y. So essentially, the product of a large and a small quantity and the product of a small and a large quantity will not allow me to cancel any term on the left hand side. Is that part clear? So I cannot neglect any term on the left hand side based on our understanding, our description of the system. Any question? Okay, but if you look at the right hand side, since the second term is quite large in comparison to the first term, I would be able to neglect the first term on the right hand side. As a result of which, this is what would be the governing equation for laminar flow inside a momentum boundary layer close to a surface. So these are the well-known boundary layer approximations, and this equation needs to be solved in order to obtain Vx or Vy. Now, why do I need to solve this? Because my aim as an engineer is to find out what is the drag force exerted by the flowing fluid on the solid plate and vice versa. In order to obtain the force, I realize that at the interface between the solid and the fluid, it is the shear which is trying to bring the fluid to a rest or imparting a motion to the solid. So I need to find out the shear force, and that shear is essentially viscous shear, which is the drag force. We also understand that in order to obtain the shear force, we need to find what is the velocity gradient. Because if it's a Newtonian fluid, then that shear, which is drag, would be minus mu times del Vx del y, evaluated at y equal to 0. That's the shear. And you multiply that with the area and you get the expression for the shear force. So everything hinges on finding out the expression for Vx and how would it vary with y and so on. Therefore, it is important to solve this partial differential equation either analytically or numerically, or take some other approach which would give rise to the shear stress at the liquid solid at the fluid solid interface. That's why we need to solve this equation, and we would spend some time on the solution and more importantly on the relations, the well-known relations which one can obtain while working with this equation. So there are several methods. The exact method, which tries to solve it analytically, and in conjunction with some numerical part, it's known as the exact method is the Blasius solution. There are approximate methods which, instead of taking a differential approach, that means some equation which is valid at every point in the flow field, I would rather define an average over the entire thickness of the boundary layer. So that's an, can you see the last line of my slide? Because I cannot. The approximate method, can you see that?
No, sir. But we
Okay.
can read it.
All right. So let's go to this. So the approximate method is the momentum integral equation. So we'll spend some time on the exact method by Blasius in conjunction with a numerical solution, which has been provided by a scientist called Haworth, and the approximate method, which is the momentum integral equation. But so what are the boundary conditions that one can write for solving this equation? At a y equals 0, obvious no slip condition. Both Vx and Vy would be equal to 0. At y equals delta, that means at the edge of the boundary layer, the x component of the velocity would be equal to the free stream velocity. It could also be equal to the approach velocity if the flow is taking place over a flat plate. And at the beginning, at the just where the flow is about to come in contact with the solid, the velocity is simply going to be, in fact, this should not be u infinity, this should be equal to v, the approach velocity. Okay, so these are the three boundary conditions which are used in order to solve this equation. So these are the three boundary conditions that one can use, but we are still have to define what is the boundary layer thickness, which is going to be less prone to error, experimental error, and that's what we are going to do in the next class. Do you have any question up to this point? Okay, if not, I'll stop here today after giving you just a glimpse of the boundary layer thickness, some fundamental definitions, the governing equation, the boundary layer approximation, and the boundary conditions. So we'll meet again on at the next class. I think that would be Friday. 20, yes. Okay, any other question that you may have? So if you do not have any question, then I'll end this class now. So thank you.
Thank you, sir.